Um, Whenever anyone wants to just design an artificial intelligence system, he would just need to think what is intelligence and need to define the intelligence for himself. And so the same happened with the pay with us with OpenNARS team. So what's intelligence and what's not an intelligence? So I will start with saying that what is not an intelligence in our opinion, and it becomes that innate behavior or instincts are not an intelligence. So that's something not is learned, that's a given to you for granted. So if a computer system, for example, in exhaustive search, so whenever you try to choose and see every single element, every single item to see if it's the item you need or not, if you in a search, for example, so it's also not an intelligence. You're just doing it one by one, choosing the item. So, for example, basic information retrieval is also not an intelligence. It's just similarly to exhaustive search, you try to find the information which is needs for which suits your needs. Now, any repeated routines like computer functions are also not intelligence. And of course, algorithms, they may be very complex algorithms, numerical calculation, sorting, fixed mapping, anything, but they're pre-programmed, they're very efficient, but it's not an intelligence. They just only say how intelligent the programmer or designer is, but the algorithm itself is not an intelligence. So then people try to interpret the intelligence. And what's intelligence according to the most of the systems, most of the people, like in mainstream AI. So basically, mainstream AI treats intelligence as a collection of problem-specific and domain-specific parts. Um, Intelligence becomes applied to the specific domain and to specific problems, like, for example, computer vision or deep learning stuff. It can recognize the static images, sometimes video, whatever, but it only applies to that domain. If you want to apply it to some other domain, at least it has to be retrained. Now, in AGI, the intelligence is basically the general purpose capability that should be treated as a whole. That's what most AGI researchers has agreed to use the intelligence in that AGI context. However, the AGI researchers still include different research objectives and strategies. In our assumptions as OpenNARS team, the intelligence is just the capability of the system to adapt to its environment and to work with insufficient knowledge and resources. So intelligence is nothing inborn, nothing given for granted. It's something basically learned and something that allows a system to adapt to environments to apply to different domain. That's what intelligence in terms of our perspective. And of course, it has to conform with insufficient knowledge and resources assumption. And what is that? It means that basically resources are always finite. We always have finite processing power, processing power and memory. We only have the finite resources. They always work in the real time, and the always system has to be open for anything that to come to it. So system has to be responsive, has to be open to any single task which nor the system knows about it in the future. And after defining that what we really want to achieve, so there is some framework. We come up with the framework. So in the very high level, how the system has to look. So the system has to have some language for representation, for knowledge representation, for example, for environment representation. It has to be some semantics of the language or meaning. So whenever you try to deal with different inferences or different premises or different statements in the language, has to be some rules for inference rules. And of course, it has to be some memory, such that background has to be recorded and the system has to have any experience. And as a final step, it has to be the control mechanism. Control is something that allows everything to happen, everything to run in the real time under assumption of sufficient knowledge and resources. That's a very difficult task to achieve. However, the advantages are, so there is independence of the domain. So the system can be adaptable to multiple domains, and it has the rich expressing power. So all the rules can be justified, and so the traceability, whenever the inference is made or decision is made by the system, it's traced. And of course, there is a flexibility of the combining the rules. But the control is very hard thing to achieve. There are issues, however. So theory is good, but the fundamental issues are such that having that insufficient knowledge and resources, we understand the resources are always finite and they cannot achieve the 100% correctness of the derivations. That means that that everything is just true to the point, and that means that basically we have to define what is the validity and rationality, and it becomes really the relation becomes relative to the available knowledge and resources and system background at certain time. So what we want to achieve actually is just to be general, to be really adaptive, flexible, robust, and scalable. Those are really the desired features which we want to achieve in the control of any AGI system. So what is Nars, non-axiomatic reasoning system? It's basically the system consists of two main parts. It's a logic part and the control part. And the logic part is the term logic. Nars is fully based and fully conforms to the assumption of insufficient knowledge and resources. And it has the design meta level as in null, for example, languages, and it has the object level, which is all the concepts and basically implemented within the control. Now we can start a little bit more detail, but that's meaning that it's a term logic basically. The Nars is different from the predicate logic because it uses the categorical statements on sentences, like here, for example, inheritance sentences, and it uses the syllogical inference rules to make an inferences. So the main things in Nars are the terms and the statements in the logic, I mean. So the term is a word, and basically it can be seen as a name of a concept. And the statement is basically the relation between the terms. In this case, in general case, it's the subject copula predicate. So on the left, you see here S and the error to P, and basically error similar to implication, but it's not in this case. It's called inheritance here. This is a relation copula. S stands for subject and P for predicate. In English, it easily can be, for example, seen as the S is P or S is kind of P, which will be introduced later. And the example here is water is liquid. So we can say here that S inherits P. And those types of terms later we will call the narcissist statements in Nars, which is basically the language which will be operated on the Nars implementation. As a one second, as a very beginning statements, basically they don't have any truth value in this case. And this is the very foundation for all of the logical layers to be used in the future. We can say it as the logical layer 0. So for that, we have to define the experience of the system. So let experience K be a finite set of the statements within the system's memory. And let we have all the beliefs like that K star, which is a transitive closure, which means using the deductive rules, we can achieve all of that, deduce all of that other statements from that experience. And then we can say that the statements similar to S inherits P or water is liquid is true if it is either in the K closure in the master set of all of the statements within the system, or basically the term inherits itself, which makes the relationship reflective. Yes, by the way, inheritance is reflective and transitive. If neither of these conditions is met, so basically the statement becomes false. And this is for the very basic 0 level logic inference. It's also important now to mention that having an inheritance relation, the term is important to the system knowledge, but it's much more important at its relationship among other terms. And so the relationship among other terms are participate in extension and intension. So there is kind of definition here. So the extension of a term is something, first of all, it has to be within the system knowledge vocabulary, and it has to be before the term. So it has to inherit the term, like on the left here, like for example, S inherits P, and S is an extension of P. The very similar definition of intension, but vice versa. So intension has to be on the right of the term. So if S inherits P, P is said to be an intention of S. And if we imagine all of the concept, whoever has, for example, just introduced inheritance relationship, organize some of the sets of the extensions and intentions, and that's actually the meaning for the system, for the Nars system. That's a kind of evidence the system has acquired. And of course, this theorem is very trivial to prove. Basically, it means that if S inherits P, if and only if the extension of S is a subset of extension of P, if and only if as an intention of P is a subset of intention of S. In the question, we can deliberate it after. So now we come to the evidence. So extension and intention really shows means the evidence for the system. And now we can kind of see and measure the evidence. There are positive evidence, negative evidence, and total evidence. The positive evidence means basically that if there is extension of S and extension of P, and combined with intention of P and intention of S, that's the positive evidence. So over here, these are the green squares. And as you can see, so this green square can be any term, for example. So it inherits S and it inherits P. And it also, intention of S is that upper top green square. So S inherits that green square and P inherits that green square. So those green is basically the positive evidence for the given statement. S inherits P is a statement. Now, the negative evidence in something which is extension of S not including extension of P, and intention of P not including intention of S. So in this case, we can see just a trivial example. The red squares, like the P, the intention of P is that red square, but it's not in intention of S. As the same as the red square is actually extension of S, but it is not an extension of P. So it cannot be contributed as a positive evidence. And now we have defined the positive and negative evidence. And now we can combine them to have a total evidence. Basically, green squares plus the red squares, that negative plus positive evidence becomes a total evidence. So now we have come up already with a metric just to somehow to measure the experience of the system, to measure the evidence of the statement. And that comes us to the meaning of the sentences or the statements. So in Nars, there is a truth value. But in general case, what is the truth value? Traditionally, the truth value is basically is an agreement with reality. Basically, how close it is to the object in the fact. So we have the description of the world, and we have the truth value or the truth of that statement, and how close objectively it's to the description in the world, to the object in the world. In ours, the truth value of the statement just measures the evidential support. So it indicates how close it is to the evidence. And that's a difference, it's already related to the evidence. Now we come to the how in Nars the truth value is defined. The truth value of the statement is basically a pair of real numbers. The range is 0 to 1, and it measures the evidential support of the statement. So the pair is the frequency and confidence. Every statement is being assigned a truth value. either is an input or derivation, the mechanism of assigning the truth value for every statement, except for the for the Golok questions. And frequency is nothing but the positive evidence divided by total evidence. Basically, if we go back, so we have see all just the green squares over here divided by the all of the squares over here. In this case, probably 2 by 4. And the confidence is nothing but the total evidence divided by the total evidence plus some other constant. For the constant, we have chosen the 1. It's just 1 for the constant. I assume there was a multiple test for that, and 1 is probably the best describing constant here. So the frequency is frequency just say about that about the truth of the statement, but the confidence really says about the how the matter of belief and the truth value. So how confident the system is in a certain statement, and sometimes the confidence is more important, actually, in more times than the frequency, because this kind of information collection or evidence or knowledge of the system, this can be look like that too. Now, every derivation produce some stream of statements, and those statements are being assigned the truth value with frequency and confidence, also within always within the range of 0 to 1. Whenever there are inferences, so there are special inferences rule defined in Nars, and each inference rule has an accompanied truth value function. So inference rule produce the derivation, but the truth value of the derivation is being computed, evaluated by the truth value function. And now we come here to the design, how it will work a little bit. So all of the rational numbers in the system, we try to basically interpret as the Boolean. And for that, we need to extend the Boolean operations, not, and, or, such that they can be mapped and applied in the rational domain. Whenever we have treat them as Boolean, we're just using the truth value functions, and truth value functions under the cover using basically those extended Boolean operations in different configurations to assign a truth value of the derivation. And extended Boolean operations are defined over here. It's basically not, and is a multiplications, or is like that. And combining those would create us the evaluation of the truth values for the derivations. So the basic, very basic, 3 inference functions are deduction, abduction, and induction. And what it does is basically given 2 premises, as here, M inherence P and S inherence M, we can produce a derivation S inherence P. Here in the left bottom corner, there is basically the truth functions. Frequency of one premise multiplied by frequency of the other premise, and confidence equal confidence multiplied by confidence multiplied by frequency of the one, frequency of the second. This is nothing but the end function, extended Boolean end functions defined over here on the previous slides. And this is basically the truth function for the deduction. There's an example over here. So if bird inherits animal and Robin inherits bird, saying basically Robin is bird and bird is an animal, and those on the right, this is the frequency and confidence value, 1 and 0.9. Those are default. When you enter the system, there is a default, by the way, system assigns itself default frequency and confidence. The system derives that, okay, if Robin is bird and bird is an animal, then Robin becomes an animal too. And it's that's a derivation statement, Robin is animal, and it assigns frequency, which is 1, and confidence, which is 0.81, using those truth functions on the left corner to get those numbers. This is actually the schema like S inherence M, M inherence P, and just derives that S inherence P. That's for the deduction. For the induction, these are teleological rules, by the way. For the induction, very similar. So we have M inherence P and M inherence S with some frequency and confidence. Then the system can derive that S inherence P. And those on the right top, those are the truth functions for the induction, how that frequency and confidence are being computed. So the example is here that Swan is a bird, Swan inherits bird, and on the right there is frequency and confidence, which are default values. And also there is another input, Swan is a swimmer. Then system basically derives that bird is a swimmer, bird inherits swimmer, with that frequency 1 and confidence 0.445 by using those truth functions. Now the last, important, like basic teleological rule is abduction. It's similar to the inverse induction. It basically, if P inherits M and S inherits M, look like the triangle here goes up and here is going down for the induction. Then basically system can derive S inherits P and assign its frequency and confidence by the truth functions in the top right corner. And again, there's seabird is a swimmer and gull is a swimmer. The gull becomes a seabird with a frequency of 1 and confidence of 0.45. Very similar, but inversed. Deduction, induction, abduction is the example of the forward inference. So we always need the belief tasks or two premises to create the forward inferences. But what if we have premises which have the similar meaning, but not overlapping evidence, come from different background, for example? So we have a revision. There are two premises which are same, but they don't come from same sources of evidences. So in this case, we need to revise them. And to revise them, there is a revision rule and a revision function for the truth value in Nars. So if we have, as here we see, S inherence P, it's one statement from one source of evidence. S inherence P is another statement from another source of evidence. And we have to combine them. And combination is basically made by those frequency and confidence formulas over here. That's how the revision works. The example is here, bird is a swimmer, bird is a swimmer. It becomes the same, bird is a swimmer, but as you can see, here is a positive, here is a negative, basically 0 frequency and 1 frequency of 1, and becomes basically the frequency changes considerably and confidence too. In revision, confidence always higher than in the premises. Revision is part of local inferences. There is also the choice rule. The choice rule, for example, revision works when the sources are different evidences. So there is no overlapping evidence. However, what to do where there are overlapping evidence? That means that two same statements come from the similar evidences. So in this case, we have to choose. And the choice rule, we will explain later, basically using basically using truth expectation functions is we pick to choose the correct statements for the system and store it in memory for the future. And the revision and choice are basically the types of the local inferences. It's been explained here. Now the forward inferences are, as I explained, two beliefs or two premises, belief in a task. Basically, there is inference between them produced by the functions of teleological rules, deduction, induction, abduction, and those being extended for the future nulls. And there is also the backward inference. Backward inference is actually to, first of all, the choice rule is the just one case, special case of the backward inferences. And also the finding the goals, achieving the goals, or finding the answer to the questions is another type of backward inference, such that we can have to find the question find the answer to the question, which is the question itself. But that the question itself, if we answer that, we can answer that master question. And this becomes, using the forward inference rule, we can now apply forward inference rule to achieve the backward inference. We can cover that like in the later session today, forward, local, and backward inferences. Now, as we defined in the framework for the AGI system, we need some memory structure to hold or to keep all the necessary informations. Whenever anything enters to the system, it becomes a task. So it can be question, a goal, or it can be just piece of new knowledge, which is considered to be a judgment. Beliefs is basically the accepted knowledge. So knowledge enters the system, the being processed, and then converted to the belief. Tasks and beliefs are basically clustered into the concept, each named by the term. So concept is named by a term and has the links to the tasks and the belief tables inside of them. And the concepts are basically prioritized in the memory. So there is a main memory. It's organized like a priority queue, and concepts are being, there is actually the priority value assigned for each concept. Priority value indicates how important this concept to be chosen. And the takeout operation from the memory is taken as the priority, probabilistic priority, priority which is probability to the distribution of the priority of the memory. Basically, what that means that the higher the priority, it has the higher chance to be taken out. However, the low priority items also can participate in resource allocation and can be taken out also. So that data structure is used throughout the systems. Main memory uses that data structure. Basically, we call it bag. It holds the concepts. Inside the concepts, there are also the same data structures called the bag. And the tasks is actually, there is a task bag inside the concepts. And the belief are basically just an array, just a list of the beliefs which are sorted by the higher confidence value from the truth value. So that's how the memory looks. Over here, we can see those like memory can be seen as the graph, where the links are basically the relationship between the concepts. Those concepts like ghoul, swimmer, robin, those are named by the term, and those and those errors means the relationships on them. They can be viewed as the weighted graph using the truth value, but in reality, it's much more complex. There are also links there. But as an easy representation of the memory, it can be just looked at as the concept as a nodes and edges as the relationship between them. In this case, we're only covering the inheritance relationship, which is the very basic level of null. What is important is that the concept is actually the fluid. The meaning is determined neither by reference nor by definition, but by experience relations. So meaning of a concept can change because the truth value can change. Also, the budget of the concept, which is the priority, can change. And that becomes that each relation is mattered to a degree. Also, the meaning of the concept can be changed in the future derivation by the history and the context of the system memory. So it also flows the meaning. It's nothing concrete there. It's always changing in the real time with the system cycles participating in the derivations. This is the very brief and very high level overview of architecture, the routine architecture actually. The user over here can input any task, or it can come from other software, it can come from other protocol. Then task is being entered to the buffer. In buffer, it's being selected by priority and moved to the memory. In memory, the local inference can happen such that it may produce more concepts, and truth value can change in memory. Then from the memory, actually, it's being taken out by priority to the inference engine. Inference engine just makes an inference on the two premises, basically the belief and the task, and produce some derivation, And that derivation task or derived task can be either going to the output or again going to the buffer and repeating the cycle, participate in the cycle. This basically, that's a very high level overview of the system cycles. And system cycles going on forever, like while true loop, until someone stops it. Producing unlimited derivation, going over in the buffer, in the memory, and vice versa. So as we can see, whenever we enter a task, we're going into the memory, it always interacts with the belief whatever system has. And it does it by applying some rules, inference rules, deduction, abductions, truth functions, and some other budget functions. All the beliefs and all of the tasks are being selected from here, from the buffers, probabilistically based on priority, as I explained. So the higher the priority, the bigger the chance to be selected. However, the lower the priority, it also has some chance to be selected. And the priority is nothing but, actually, priority is, priority is something which is the short term and long term. For the priority stands for the short term, and the quality for the long term importance. And the quality is basically how useful the item becomes in the history and it's relevant in the current context. So priority of the item over here is not just a single rational number, it's actually the composition of rational numbers. Some of them means a different thing. One means that the short-term importance, how important it's as of right now, and the other one is the long-term importance, how important the item is in the long run, which means that if the long-term importance of the item is really high, that the item is not being forgotten, removed from the memory. And that long-term importance is called the quality. As we described now, we only covered idealized logic level 1 over here, or its implementation null 1. There are 9 levels of logic, each of them added upon the next one. Because basically the system was started from the design null 1, then added null 2, null 3, null 4, and etc. Each of them has the basis of the null 1, but in addition, it adds the truth functions, it adds the inference rules, it adds it's a different functionality for the systems. For example, in null 2, there are introduced the set elements such as instant properties and similarity copulas. In null 3, there are set operations. In null 4, there is regular relation. In null 5, there is, for example, there is already statements as considered to be as a term itself. In null 6, there is a variable. Null 7 is for the temporal inference, such that the statements can be considered as an event. Null 8 becomes that procedural learning, and null 9 is not yet fully implemented, but we're working on it. It's basically self-control. That's what it says over here. So basically, the higher we go, the more advanced the logic becomes, but it still has the basic similarity with the easy ones. So inheritance copula, the variance of inheritance copula is similarity, instance, and property. This is for the null 2. For the null 3, then we introduce compound terms and term complexity, which basically relates to the sets, intersections, difference, products, and images. This is now null 3 and null 4. There are new inference rules added, like comparison, analogy, and some structural and compositional rules, which allows the terms to be restructured or compose the higher complexity terms. Now, as a higher order reasoning, we're starting with null 5. The introduction of the statement as a term. New copulas also introduced, like implication and equivalence. Negation is introduced, conjunction and disjunction introduced. By the way, conjunction and disjunction is introduced in the way similar to the intentional and extensional intersections. Conditional inference as implication. And what else? It's in null 6, we have implemented the variables as a terms, as a symbols. So null 6 is for the variables. Later on, basically, null 7, we introduce the time to the system. So each of the truth value has been assigned a timestamp, and the statement becomes an event and a statement with temporal relations. Either is sequential or parallel. That's a higher level null 7. Then null 8 is the operation as executable events with sensory motor interface. So also the goal and planning introduced in null 8. And the mental operation are introduced in null 9. We have the list of hard-coded operations for the null 8 for the procedural learning. And also in the null 9 is basically the self-control, which is still under work. Now, as we see, the Nars is fully based on assumption of insufficient knowledge and resources. It basically has a unified representational language. It has a complete inferral power. It has reasoning as learning, planning, problem solving, and decision making. It can be integrated with other software, and it has the plugin interface to be available as plug and play for the other software. There are the main implementations of OpenNARS. Is mostly implemented the OpenNARS for the research is a Java version. So this is the main implementation, which we all work on. There are also their implementation, Patrick done another implementation, OpenNARS for application. He will demonstrate it later today. And there are multiple working examples exist as proof of concept for OpenNARS. As we can see, the system really shows many people-like, human-like properties, but it's not deemed to be psychological model. So no one really tried to achieve the same level of psychological thinking or cognitive science as a human process. And all of that what discussed really brings NARS to the potential applications. NARS is not defined for anything specific. There's no the specific applications. There is none. It just can be considered as a general purpose tool. It can be suitable for multiple domains where assumption of insufficient knowledge is applicable, where tasks can be expressible as reasoning, and where some other software can have compatible interfaces and require some insufficient assumption of knowledge and resources or tasks which can be expressed or reasoning. So NARS is very kind of adaptive to the environment, can be used in many things, but not for any specific domain. And this is, we go to the end. All the publications and reports can be found over here. Source code is opennars.org. Also on the GitHub, there is a wiki pages that comes in more detail of how things work and describe the functionality of NARS. Any questions? Until we can go, or we can go after having like control overview. Any thought? Okay. So this was the general overview of NARS theory and how it works. Now we can go to the implementation, which is the OpenNARS implementation for research. Yes?
In the chat, there is a question.
In the chat, there is a question.
How does the system learn the bottom level concept?
What do you mean by bottom level concept? So basically,
hello, sorry, I mean the bottom level concepts like swan and bird, like which are on the bottom atomic concepts. Are they
those
programmer?
Those are being entered at the very beginning. The NARS has no information about anything, so it's the knowledge is completely empty. So someone enters the statement like bird, like Robin is a bird, right? And that statement is processing. It's a statement being converted to the task, and task is being processed. So far there is nothing in the system, and the first concept to appear there will be the Robin, the bird, and the Robin is bird as a task. That's how the first input is being entered to the system. Where is that? 1 second. Over here. So basically, this is the input statement, right? Goes to the buffer, and then they're going to be processed and decompositioned in the concepts, then put into the memory. This is the bottom concepts, as you mean, right? Now the second statement enters. For example, bird is an animal, right? So it enters the buffer, again, decomposes to the concepts and put to the memory. So there are revision mates, local inference mates over here. It may be more concepts created because of the local inference, but now it's become 3 concepts. The bird is already there, so we have to revise that. In another concept, animal, right? So now it becomes a 3 concept over here at least. And it's being then choosing from the memory into the inference engine, right? And into inference engine, we'll do some inference on that using the rules like abduction, deduction, induction with the truth value functions. And then we'll create some derivation like Robin is an animal, right? And Robin is an animal becomes a task again. So task again will be put into the task buffer over here. Then it will be either output or also, or actually not or, and will be decomposed again into the concepts and put into the memory. Does it answer your question?
Yeah, thank you very much. This was a helpful explanation how it works again. Thanks.
Yeah, I have a follow-up question. So when you calculate, well, I'm not sure if it's called the weight or I guess the frequency.
1 second.
When you calculate the frequency, do you use only bottom concepts, or do you mix? I mean, when you're talking about the extensional part, so we have W plus when you calculate W plus. So here it's going to be this relationship. Well,
I think I understand the question.
Okay.
So whenever you, okay, so that's a frequency. That's this is more of the theoretical explanation on frequency and confidence. So how from theory we go to the implementation, right? So in theory, basically what we mean on the paper on the board, it's that we have to find the positive evidence, and then we have to compute the total evidence, right? And then to divide the ratio by the positive by the total evidence, right? And the confidence is similar. So we have to find the total evidence and divide it by 1, as you can see. So basically, if the total evidence is really high, so that number becomes close approaching 1, right? If W is really high. But if W is really low, so that's confidence is approaching 0. How it is done? Go for this diagram. So as you can see over here, I input the statement into the buffer, right? And by default, I have applied frequency of 1, but it's just a default parameter, and confidence 1. With those truth value 1 and confidence 0.9. With those default truth value, it goes to the concept to the concept memory. Now the next statement also goes with whenever it's an input, for example, that has a default truth value 1 and 0.0, also going to the concept memory. When there is an inference, they already applied the truth rule, the truth function to evaluate the confidence and the frequency. And that truth function is basically nothing but, extended Boolean operation. So we treat it, so frequency was 1 and 1, we just multiply them, and for the derivation, we have the 1, for example.
Okay, well, how am I going to explain that? Well, in probability theory, when you want to calculate probability of an event, I mean, of a concept, which is a set over the sample space.
Okay.
You're going to consider a partition, which is going to be the lowest level partition you can get, and you're going to have a mass function over this partition. Well, you can consider the how to say the members themselves, but if you don't know the sample space very well, you don't have to do that. You just consider a partition, and by doing that, you ensure that you're not going to count multiple times duplicates. Basically, if you have a partition, is going to prevent from having basically two elementary concepts that would overlap.
Mm-hmm.
And so I have
you
a
want to
hard
know
time seeing how that is done in Nars, basically.
In Nars is a little bit differently. So everything is grouped within the concept itself. So the concept is named by the name. The concept has to be unique there. And whenever you choose the concept, right, from that, where is that diagram? So here in the memory, over there, whenever you choose the concept, basically concept inside of it has the pointers. So one pointers point to the task, whichever concept is associated to. And that association was built whenever the task was first input to the system. It may be just input or a derivation. So over here, for example, after the inference engine, the task is created, then it's being decomposed by the concepts. And those relationships are being established. So every concept has a pointers to the task it's associated to. Also, it has the pointer to a term which is associated to. So for example, Robin is a bird. Robin inherits bird. This is a task. And also there is a concept Robin, concept bird, and also there is a concept Robin is a bird, right? And all of them has the pointers to the task Robin is bird. Also, they have pointers to the terms. So Robin is bird concept has pointers to Robin and bird, right? So each of the concept also have the set of beliefs inside of them. So Robin is bird concept has a belief, Robert is bird, pointing to the task. And whenever you select, for example, concept Robin is bird, you select that. You select the task link, and then you select the belief from it. Then you select the term link, and then you select the belief from that point to that term. So there is guaranteed, there is no duplication of, as you said, of that similar concept is happening. Does that answer?
Well, I guess, well, yeah, partially, I guess. Okay, I think as things get more concrete, I might get the full picture, and but yeah, thank you.
Because
for now.
yeah, because it's a beauty of it, actually managing the resources, that formation of the concept, it's happened to be in the very first stage of task processing.
Sorry for interruption, Peter. I think I understand Neil's question. Just answer it in one sentence. The calculation of truth value in Nars is not based on probability theory. This is something I have debated with Ben for 20 years. We can talk about it later, but we don't have the time to fully explain. I fully understand where your question comes from.
Well,
yeah.
well, that's true, but we have to select the concept probabilistically to the priority.
That's a different story. He is talking about why the truth value is not calculated according to probability theory. Yeah.
Can I answer the next question?
Please.
There's a question, can Nars represent non-symbolic / magnitude values as terms, or does it handle such things differently? It's actually a bit related to the previous question, how does the system learn the bottom level concept? Essentially, what we have is, so at the bottom level, so to speak, for instance, there are sensors attached to the system, and those sensors are then going into some kind of encoder, which then uses essentially sensor terms, just terms the sensor can output. It can be something like temperature, low, high, or middle. So it can represent different temperature values with different terms, but only in a discrete way. So you can say that you can have multiple values for a given range of for a given interval of values. That's possible, and of course, often you could have multiple sensors attached, and the system can then combine those terms to more complex patterns. And this is really where the bottom level concepts come from. It's for instance, in a robotic scenario, you have some sensors, and those give you different terms, and the system can then see certain patterns of terms which appear at the same time, so it can correlate them, and so it can form higher compositions of those terms to represent a pattern, let's say Raven. But it could also be that, for instance, you have already a pre-trained artificial neural network, which already detects something like a cat. So you could have some output label cat, which directly enters Nars as a term. How deep you want to go really depends on the particular architecture, and it's not easy to say, but it seems that in human perception, our representations are to some degree introspective, so we can even reason about edges and things. We don't just see there's a cat, but we can distinguish our cat from a neighbor's cat. So it's difficult to capture this in if you just do end-to-end training from images to labels. So actually, so it's difficult topic. How much granularity do you want to allow for the bottom level concepts? Do you want to use an autoencoder and convert the latent space activations to Narcis, or do you want to have a direct end-to-end training and only enter terms like cat or car or something like that? Or do you go completely to the sensory levels and say each sensor on the retina has a range of values, and each sensor will emit an event for now to be consumed, which is so. Of course, what we currently don't allow is to say we directly enter a value. But if we talk about computer systems, even a 32-bit number is not really a number, but it's a list of 32 bits. And so it's always a question of granularity. How far do you want to go? Even in Nars, you could have something like a bit vector, but of course it's more difficult for the system to work with such a representation than with a higher level representation. But sometimes you need more granularity, and this is really a difficult topic. And we are currently trying to design sensory channels which allow to work with vision, and we are also open to combine or to use existing machine learning technology, which has proven to be very successful in certain aspects. So we are very open of how to encode information and to our system, essentially. You're welcome. Are there any other questions, or should we continue with the next presentation?
Okay. Shall we continue?
Okay.
So basically, one second. Over here, we have the overview of the OpenNARS implementation for research, implemented in Java. Source code can be found on GitHub on OpenNARS.org. Wiki pages are also available on the GitHub. So whenever creating the OpenNARS, it has the logic and control parts, and the control is really, really difficult. That's why the development of AGI system is still very difficult task to do. So these are some of the control criteria for the OpenNARS for research. It's as we said, it has to operate under assumption of sufficient knowledge and resources. And NARS always expect new tasks to arrive at any given moment in time. That means that system always has to be responsive for new inputs and new derivations. It also means that the space of data structures are always bounded in size, always full. And there's some eviction policies has to be in place. Also, the control has to work in real time. That means that the operating cycle has to finish in a constant time, roughly in constant time. That means that all of the items has to be important to the derivation context. All of the items has to be important to the knowledge of the system, and some short and long-term importance has to be introduced for the items, such that we can select an item as we need it right now, and we can keep the item for the history as we will need to select it like in a while. But it should not be. It should be there. It should not disappear. However, if the data structures become full, there is no place to put the item, so it has to be implemented some mechanism to forget the items, but the item has to be forgotten such that we make sure that the item is no longer needed. So that all lead to the creation that's of the high-level overview of the control mechanism. So it has multiple buffers as of right now. We're currently working on the implementation of the global buffer design, but as of right now, the code is implemented in this way. So we have the input buffer, derivation buffer, main memory on the right here, all of the functions, truth, Boolean, budgets, functions, rules, local logical rules, inference rules, local inference, compositional structural, and of course the inference engine. So this is the more detailed diagram that was on the previous presentation. We have the event back for the for the events. And this, now we will talk how it all works. So the memory on the right here of the concepts, as we see, is basically as a memory of concepts. It stores the concepts, and the stores in the data structure we call bag. It is priority queue, and it has operation defined as put, get, and get by the key. Now the get operation gets the item probabilistically by priority, proportional to the priority. So the bigger the priority of the item, the bigger chance for the item to be selected. And however, the low priority items also can be selected. So they also can participate for the resource management, for the resource allocation. The bag is limited in the size. And whenever the bag becomes full, the data structure becomes full, the lowest priority item is being removed from the bag. And that happens quite often because the Nars derives multiple hundreds or even more derivations during the cycles, and the bag actually becomes full and elements have to be removed. There's no space to store them. The bag actually is just a data structure we choose throughout the system. So it's in the memory, it's main memory, I mean, it is the concept inside, is in the buffer too. So Basically the most important data structure used in OpenNARS for research. We didn't speak about budget values, so all we mentioned is the truth value. We know that truth value is frequency and confidence. It's just basically a set of two rational numbers, which shows the positive evidence for the frequency and the reliability for the confidence. But how the item has to be selected from the memory or from the bag is basically the work of the budget value and budget functions. So the budget value is a set of three rational numbers. They are also in the range of 0 and 1, and they are assigned to each data items. They're only not assigned to the beliefs, but they assign all the links. So over here, we have the memory of the concepts. And in the previous presentation, we've seen that they connected by the relations, like Robin is a bird, inherits bird, and that's a relation that connects to concepts. But in the real world, I mean, in this implementation, actually we have many links that connects throughout that concepts: term links, task links, and belief links. And the priority in the budget value is being assigned to everything but not the beliefs, because beliefs are sorted inside the concepts by the confidence value. So the priority of the budget value of the item basically means that how important the items right now. Whenever I need to select, I'm going to select this proportionally to the priority. If priority is high, I'm going to select it as a very high chance for the item to be selected. Quality, on the other hand, that indicates the long-term importance of the item, and that the bigger the quality is, the ideally the item is longer not being forgotten. Now there is a durability also. What's durability? Whenever the item using the priority being picked out from the memory over here, right? It's then the task and beliefs and participate into the inference, so they become two premises, and inference happen to be on those two premises. Now they are returned to the memory, back to the memory after everything is done, after decomposition of the derivation task is done, as we described previously. So eventually they return back to the concept memory. However, the item has been already participated in the inference, so the priority has to be decreased, otherwise it will be picked up again. So the durability is basically a hard-coded hyperparameter. It's basically a decay rate, which is multiplied by priorities also in the range 0 to 1, and it just decreases the priority of an item after each of the inference cycle, such that priority decreases until the priority reaches the minimum, and if the data structure is full, this item is being forgotten, removed from the bag. Now, each concept can be represented as on this picture. So we can see, we can see in the main memory, there are dots actually the concepts, and each concept is have two things. So concept is the way of storage, and constant is also the inference entity, as described before. So concept is taken from the memory, and it has all of the necessary items to accomplish inference within it. So it has the task link bag is basically the data structures the same data structures that used for the concept memory, but it stores the links to the tasks. We will go over it later. There are term links, whereas basically the links to the terms. For example, Raven is bird, that's a concept, and it has a term, which is also a concept, Raven and term bird, and the term links going to point it to the Raven and bird from here. And the task link is going to point to the Raven is bird as a task. And that really makes the efficiency of the choice. We don't have to exhaustively search all of the concept network to find for the elements which has to participate into the memory. We just select the concept, and following the links, we select the premises. Then whenever we do the derivation or inference, we put all of the constants back with adjusted budget value. That's how the derivation works. It also has a table of beliefs, and table of goals. So for the beliefs, all of them are basically sorted by the confidence value. So there is no budget. We just take the one from the top, the heap-like structure. And that would bring us to the cycle, how it's going to happen. So Nars always operates in an infinite cycle. So it gets something from the memory, does a derivation, puts something back to the memory, gets something from the memory, creates some derivation. If the derivation is true to the is a relation, and then puts back to the memory. So that's how it works in particular. So from it puts the derivation or inputs to the global buffer, which we're going to implement into the memory, then triggers the local inference, which is revision for the related concepts. The next, basically, we select the concept from the memory, from that memory, the right dot. After that, we select the task link, which points to the task from the concept. So from the task, we selected the concept, when we select the task link from here, which points to the task. Then we select the term link that goes from the back over here, that goes to the term. And then from the term, whenever the term link points to, we select the belief. And the belief, so that basically term link points to another concept. Inside the concept, there is a belief table, and belief table has the beliefs associated with that concept, which are sorted by the confidence value. And we inevitably select the highest confidence belief. And this becomes the second premise. The first is a task, and the second is the belief from the concept where the term link points to. Then we do some inferences on those two premises, applying all of that inference rules and truth functions to modify the truth value. Then we do apply some budget functions to apply the budget, to modify the budget value, which is priority, durability, and quality. Priority has to decrease, and quality has to be recomputed, depends on the situation. And then basically we also input the conclusion into the global buffer. Then it's going to be again created, again processed, put to the memory, and the operating cycle starts again and again. And that's operating cycle, we call it, it completes roughly in a constant time. Because of that selection, because of that grouping, everything is inside the concepts and the pointers, it always kind of does it in a roughly a constant time operation. This is how the time is being measured in OpenNARS. Now, I want to say the difference between the task and the belief. So sentence can be stored in the memory as a task or a belief or both. So however, the belief can be only judgment. So judgment needs to be processed and absorbed by the system and turned into the beliefs. So belief is a judgment that already has been absorbed by the system and will be used to process the task. It is be used as a premises to participate in the inference. And the task is what to be processed by the system. So system processes the tasks. And this is example of the task processing by the system. So the sentence can be entered by the user. It can be derivation, can be anything. So it enters the system the sentence. For example, a raven is kind of a black thing. Over here, the system attaches it the truth value. In case of input, there's going to be default. In case of the derivation, the truth value has to be computed using the truth functions, which are associated with the derivation functions. Now, the task object is being created. The task object has the same name as the sentence. Raven is black. Task is being put to the task buffer over here. Okay, over there in the derivation buffer, or in global buffer for the future. So then the sentence object is created, and there is a pointer from the task to the sentence object. So all the terms within the sentence are parsed, and concept related to the terms are being created or updated. So for the raven is black, there is terms raven and black. The concept for them are being created. If the raven, for example, is already existed, so it's being revised. And all the links, as I mentioned, task and term links are being created, or budget on the links are being updated. Then the budget, finally, budget value is being derived for the tasks, or it can be default if it's an input tasks. And then task is actually put into the concept memory and it's ready to be selected. That's how task is being processed in an OpenNARS. This is an example that make it clear what's the difference between task and term links. So over here we have the task entering the system Raven is bird. This is a task in the orange. And the bird is an animal. Two input tasks we have, for example. Those truth value is default because it's an input. Now the concepts are being created. Task concept being created, Raven is bird, Raven and bird. And also for the right task as bird is animal and animal. From Raven is bird, there is a task link. And from the Raven and bird, there are also task linked to corresponding tasks. So from the Raven is bird, there is a red link, task link to the Raven is bird tasks, the same as from the Raven and from the bird. But from the bird, there is another task link to the bird is animal. And the same from the bird is animal and animal. So whenever I select this concept for the participation in the for the inference, I would have two items into the task bag to select from. Then also the beliefs link, term links are created. The term links is basically in blue here. From the Raven as bird, it has the two terms inside of that related to that concept, which is Raven and bird. And notice that have the two, it could be bidirectional links, but it's actually two different links. So from Raven and bird, there are two different links from Raven to the Raven is bird and vice versa. The same is for the Raven is bird and bird and animal, and bird animal is an animal. The reason for having two different belief links is because everything but the beliefs itself have the budget value attached. So I'm sorry, it's not a belief, it's a term links. The budget for the link from Raven to Raven is bird often differs from the Raven is bird to Raven. That allows different participation or from the inference within the inference cycle. So this is the difference between task link and term link. Now those are the basic up to null 5, I would say, so logistic rules which are used into the inference cycle. Each of the rules has the related truth functions. It can be found online, the exact formulas. There is no sense to put them here. But whenever we select concept, we select the task and we select the belief from that concept. So basically, we apply one of those rules onto premises, and then we compute with the corresponding truth functions. We compute the truth value of the system. After that, we basically adjust or create the budget value, attach the budget value to the sentence. What also there is in the system, there is extended Boolean operation, which we mentioned. Every rational number is treated as a Boolean number, and we try to try to make an operation similar to the Boolean and, or, and not. And also there is like utility functions also, like some of the special cases of the maxes, mins, or truth expectation, for example. Truth expectation is not basically the utility functions, but something which allows the choice rule to function properly and the budget value to be computed properly. So truth expectation is, although the truth expectation can look similar to the truth values is summarizes the evidence in the past which is collected by the system. However, truth expectation is basically can predict in future how the statement will be valid in the future. So if the truth expectation also in the range from 0 to 1, if truth expectation approaches 1, it means that a certain statement is always be true in the future. If it goes to 0, it's not being true. And that's how it's computed, being that formula over here. And it's used as a choice rule. So the higher truth expectation then means that that statement is being selected whenever the choice is being from the statements with overlapping evidence. Truth expectation is always also used to create, to compute the quality from the budget functions. So that's over here. Quality. There is a utility functions called truth equality. It can be considered as a budget functions, but mostly utility functions. So having the truth value of the item, we can apply truth expectation to create a single truth representation of the statement, and then having that, we can create the that we have computed to quality. Now we come to the budget functions, because budget functions is really important stuff in the Nars. So basically, the meaning of the statement, it's evidence summarized by the truth functions, and its importance by the budget. If the statement is not true, it's useless. It gets only negative statements. If statement has the low budget or low priority or quality, it would never be chosen to participate. So nothing will be derived using that statement. So the meaning comes from the both truth value and the budget value. And the budget functions are the functions that modify the budget value. So the main function is the budget and inference, which creates a budget for derived task and also updates budget for selected concept term links. Budget value is a little bit tricky because, if you can see here, budget value is attached to the concepts itself, to the sentences, it's up to the term links and to the task links. And computation for them is really different, because it's really different in terms of what is premises, what are the premises in a certain inference. For example, for the term links, it updated differently than for the concepts, and for the tasks link differently than for the term links. That is kind of active research as of right now, to really choose the correct budget functions that allow the item to stay as long as we need it and make the item important. So the main is the budget inference function. Then merge, we have to merge the budget values, activate. We have to activate the budget value of the concept, revise, for example, same concepts comes and we have to revise the budget of the concept. And as we mentioned, there is truth to quality, which basically converts truth value to the quality of an item. That is a brief overview of the implementation of OpenNARS. Any questions, participation is welcome. And more detailed formulas and everything is available on wiki pages, and the code is in the source code. Any questions? Chat. 1 second.
From YouTube, there's a question from Pablo Mena. What's the input format type? Plain text?
No. I forgot to mention. So Nars has a formal language called the Narcisse, and the Narcisse has a special grammar, type. I can go on over the wiki pages to see Narcisse grammars and annotations. So basically, if you want to input anything to the system, it has to be conformed with the format. And we have all the copula defined, which is a relation, and the truth value in a special format you have to enter. So basically, there is a language which always has to be used as an I/O for OpenNARS. I can put it to the chat over here, the link. It's actually under the construction, under development, how to translate the natural language sentence to the Narcisse. It's also one of the active research area, such that anyone can communicate with the system. Did it answer the question?
I guess so. Well, so the answer is yes, right? It is plain text, but you have a homebrewed grammar.
Right. The format has to be
interpret,
compliant with the Nars grammar.
Could Nars learn to use English?
We actually kind of try to figure it out, how to apply Nars for the natural language processing. Do you mean by learning English? What do you mean by that? Such that we can just type in English and it will be converted to the Nars?
Yes, I mean, if it's good at learning and it's good at learning patterns and concepts, couldn't it just be rigged so that it continues to get better and better at English?
Patrick, did we experiment with that? I remember.
Yes. In principle, we expect that natural language should be something which can especially be well handled with non-axiomatic logic, because in language you often have ambiguity and other issues where a sentence is not complete or a part of it is missing. And in the past, we tried some experiments where we essentially tried to let the system establish a meaning, a represent relation between a sentence and the concept, and so that we just give more examples, and the system essentially learns the meaning of a certain fragment. But it's so far where we failed so far is mostly from a control perspective, because the inferences get more complicated when the language structure is more complex, and so in theory it should the logic should be very suitable to reason about language, but from a control perspective it's difficult to handle it properly.
I just post a link to the chat window. You can see there is a technical report about our plan for natural language processing.
Great, thanks.
Additionally, what we also did, because there's also conventional technology, we also have created a shallow semantic parser, which simply maps simple English sentences into Nars. This is not the full story because it's parsing, and we think the idea of parsing, the idea that a sentence has only one meaning, is wrong. So this is only a preliminary, or it's something which should make the interaction with the system easier, but it does not solve the full problem of natural language understanding, where certain phrases or word combinations can have multiple meanings and mean different things in different contexts. So it's still a lot to do, but later actually you will at least see the shallow semantic parsing thing working.
Mm-hmm. So another question: can system automatically update beliefs in a way to disambiguate terms? So do you mean that there are multiple beliefs in the different concepts to the same term? Is that what you mean? So example, split automatic peacock into.
Yes, I wanted to ask if certain point you can recognize maybe that there is no consistency in the way that the beliefs are given to the system, and the most logic explanation is that the term is ambiguous.
the beliefs comes from the judgments. So I'm actually not getting the question. Terms are always, yeah, I mean, term has its own, term has a concept, right? And the belief table is inside of the concept. So it's sorted by the confidence value inside of that, all of the beliefs of the certain term.
I guess he's asking for the relationship between concepts and words. In Nars, they're separate, so there is a many-to-many mapping between concepts and words. So one word can correspond to different concepts, and one concept can be related to different words, and the relation context sensitive, so it will be updated from time to time.
Mm-hmm. Yep.
Okay, thank you.
Mm-hmm. Anything else?
Could you come back to the expected
Truth
something
expectation.
else? Yeah, and explain how you intend to use it. I mean, when I see it, I see that it is basically it's the mean of the second order distribution in some cases. When it's completely flat, for instance, the confidence is 0, and it's the result is 0.5 no matter what is the frequency. And so like exactly how do you use this formula?
Yeah. So the semantic of that is that if confidence is 0, that becomes 0.5. You're absolutely correct. And 0.5 means that the system is not really, there is no, the system is not sure. It's completely uncertain. Either it's true statement or it's not true statement. That's what the 0.5 is. For example, when evidence is 0, then the frequency is 0.5 also. The system is like unsure. So whenever there is 0.5, there's always like uncertainty of the system. Closer to 1 is that the true statement has to be hold for long. Closer to 0, basically it means that it does not hold. It's not true at all.
Right, but what about the situation where the confidence is very high and the frequency is 0.5? How are you going to make the difference?
But it's very. I see what you say. But it means semantically. That means that we have huge evidence saying to us. So many examples has been collected saying to us that that truth of the statement is not really. The truth of the statement is uncertain.
Right. It has maximum entropy.
Right.
Okay. And so
and that becomes the same for us because truth expectation needed to make a choice and create and really compute the budget.
And so okay, so the truth expectation, so it's written is used in local inference and budget. So you said that the budget is basically the amount of attention
quality,
you give to something.
Amount of quality, which is a long-term importance. So truth expectation is something to predict, well, something to predict the future.
So truth expectation is equal to quality.
There's a bigger than that. Over here, it's not equal to, but it used to. It's one of the main thing to compute the quality. So whenever we need to create a budget function and we don't have it in any, if for example we just initialize it, we need to come up with something, and we treat its truth expectation, we convert it to quality. In this case.
And is there something else than truth expectation to calculate the quality?
Yes, yes, there are,
Yeah.
for example, budget inference over function calculates everything, priority, durability, priority and quality. Okay, maybe can,
How can
1
I,
second.
can I add something?
Yeah, you can add while I open. Yeah, please.
There's this issue of how which quality should the concept really have, and there are some innate or intrinsic aspects, like how complex is the term which names it. So the complexity plays a role. On the other hand, also the truth value of the beliefs in it. So if it has something which is very true, it maybe is more important in the long term than something which has little truthfulness or even contradicting evidence. So so there are some learned aspects of quality, but there are also some intrinsic aspects based on, say, the complexity. But there are also some other factors. Quality calculation is really a large issue. There are also in Cox literature, there are many different considerations. What makes a concept more important or less important than another?
This is the high-level table. I mean, high-level. There are many special cases of that inference, but it's a very high level how to compute the quality. So, and it also becomes on the data type you're dealing with. So for the tasks or the terms are different. And this is basically how it's done. But for the initialization, the truth to quality is always used. Because first we have to initialize the budget value.
This is also one aspect which is often criticized about the system, because the logic makes easily sense, but the control mechanism is a very complex piece with many different components. Where even something like the quality calculation for concept is already something complex by itself, and so it's not easy.
Okay, so you're saying that basically the coherence of the logic requires the control mechanism. I mean, that's what I'm sort of taking.
Or at least basically the control mechanism is what decides what to pick to create further inference. Which premises do you want to retrieve from memory to derive results? And so the system needs a way to prioritize certain information over other information, and also in different contexts. And this is a difficult issue, how to make sure that what the system works on is really contextually relevant to what the system currently wants to achieve. And that's a big issue. We also have a new implementation which uses much simpler considerations, much simpler budget values and budget calculations. It works for most cases, but in the long term, especially if you want to get to human level intelligence, there might be some factors which this more complex budget system or those more complex budget functions capture, which a simple treatment may not capture. For instance, in the new implementation or application related implementation I'm currently working on, we simply say that the quality equates to usefulness in terms of how often was a certain concept used and how recently was it used. but this is not the entire story. To some degree, you also want to incorporate other aspects like the complexity of a concept, because if a concept is more complex, it also demands more time to get something useful out of it by inference, because all the activity in the system is performed by individual inference steps, which can transform some piece of information only step by step. And so if something is more complex, often you need more inference steps to come up or to use the information you have. And in that sense, you want the budget system or the control mechanism overall to favor more simple representations, which can easily be used, and it's it's essentially like a form of compression where you want the system to find more simple representations. Because if it would only work, if it would work with more complex ones, it demands more resources, and it's also more unlikely that it will be able to get something useful out of it. So there, in our experience, it makes sense that we bias the system towards more simple representations, which is also related to Occam's razor. But we don't just say simple things tend to be more true than more complex things. Instead, we justify it according to the resource usage, in terms that simple representations demand less resources to work with. And so it could be that sometimes a complex concept could be equally useful in some cases, but already finding it will be very resource intense. And so we don't buy the original form of the Occam's razor, where we say simple is simply better without a real explanation. But we say simple representations are better because they demand less resources. So from an insufficient resource perspective, we want the system to find simpler representations which are workable, and especially also if you take the real-time aspect into account. When the system works on a problem, there might be new problems appearing at any moment. So it has to take into account that each inference step it takes is itself taking some time to be complete. And so it can't just arbitrarily reason in any direction and assume that it will have.
Does it take into account the time and the resources of the inferences via reasoning itself?
Oh yes, exactly.
Oh well, that's great.
So that,
okay,
so
that's excellent.
The time is itself a factor in the resource allocation, and this is actually a very tricky part. In some sense, for instance, the bag structure we saw before, where items are simply ranked according to the priority, and higher priority items have a higher chance to be selected. And if they are taken back into the structure, their priority is decayed. If you do this, even if you don't know what operations you will do on the items you sample, if you just do this to decay items priority whenever you use them, you will have the effect that that the current items in the structure tend to be contextually relevant, because the old ones have already been selected and decayed in their priority. So there's already by this mechanism where you decay the priority of items, you get this effect that the items which currently have a high priority tend to be new items, and hence to be more contextually relevant. But of course, it's not the entire story, it's just one aspect of this entire picture.
I have maybe one final question. How do you balance exploration and exploitation?
That's a good question. We believe that essentially the right balance between exploration and exploitation depends on the context. So it has to be something which is context dependent. For instance, we don't want to say to give the system a certain search strategy where we pre-design the depth and maybe in what width it searches in. We don't want to do that. Instead, we simply have this reasoning mechanism which is data-driven, and the data items and the priority themselves decide how much the system will explore and how much it will exploit. So if, for instance, in the back structure, if you have the situation that only a few items have a high priority, then the system will naturally exploit, because only those few items will get selected most of the time. While in another situation where you have priority values, where you have a lot of high priority items on the top of the bag with similar priority, they will all have a similar chance to be selected for inference, and then you have automatically the effect that the system will explore because those have similar chance to be selected. So the idea is to leave explore versus exploit to be completely or mostly data dependent property, but it's not fully data dependent, because essentially you also want to define a mapping which maps from the priority values in the bag to the probability to be selected. And so there's the question, do you want a linear mapping, or do you want something like that there will be, that the low priority items have almost zero chance to be selected, out of being in range 0.1 or something. So there's also an intrinsic aspect of how you design this back structure, how much it favors high priority items over low priority ones. But else, that most of the balance between explore and exploit is actually a data-driven thing, which is context dependent based on the priorities which are existent in the back. So from this perspective, there's also no fixed algorithm which, for instance, would apply a planning up to a certain depth or something like that. It's part of the system can plan, but the planning process itself is performed by doing those individual inference steps. And so sometimes when the system, say, applies some deduction rules to plan ahead a bit at the same time, then it might select some other inference to find some analogy or some similarity between those structures. It's how, so there's no predetermined algorithm which says now the system should plan, or now the system should find analogies or something like that. Instead, it's completely data driven. What will be done depends on what will be picked, and what will be picked depends on the priority of the items in the bag. That's the general idea. The only thing is it's not difficult. It's not easy to get it right, because you want this system to be to some degree self-organizing, and so you don't want to impose any task-specific biases, and you want to have a general way to control the system. So, which, how to say it? So it should naturally be data-driven, but it's not easy to get this right. But overall, I can say the system beta has now shown, which is the current or the Java implementation we have, which tries to be a complete AGI system. This is very difficult to understand, but we also almost everyone in our team has his own implementation. So we also have implementations which are simpler, and it's interesting to see that even simpler implementations can already do impressive things. And but you will see this soon, because my talk will be about about a simpler implementation.
I still have more questions, but I'm worried to not give enough room for the others. So, well, if nobody is asking, so you mentioned that exploitation versus exploration is determined based on the priorities, do you characterize priority by a single number, or do you have a confidence associated to priorities because it feels that it could be useful in terms of well, assessing a good balance between exploration and exploitation?
We have something called durability, which is kind of like confidence for priority, because it says how stable is maybe not the right word in this context, but at least how fast the priority should decay over time. So it can be that a certain data item will have the attention for longer than another one. And then additionally, there's also this quality parameter, which indicates long-term importance. So if the priority of the items, say it didn't work on an item for a long time, or the priority is low, let's just say the priority of 2 items is equal, then the item with if it's a low priority, then the quality will still give the item with the higher long-term importance a higher chance to be selected, because how it's actually implemented is the priority will not fall below quality times some constant like 0.1. So if the quality of the item is 1, then the quality will not sink below 0.1. So a high quality item will not go below a certain this priority barrier. So if the items are not really, if there's currently nothing the system has to do, it will still prefer the item which has a higher long-term importance to work on, because its priority barrier is higher than the other one, than of the other item. That's an additional aspect here.
Hey, a silly question to see if I'm really understanding things right. Suppose that this Nars system was running for a while and people inputted a bunch of facts. And then suppose everybody stopped inputting facts, but Nars keeps running indefinitely. Then would it eventually just go through and exhaust all the facts that had previously been inputted into it, and then perform all possible calculations from them, and then achieve some final fixed truth values, and then just sit there indefinitely until further input was received? Or would some of if enough inputs had been received before the users stopped using Nars, then is it possible that some of the very old inputs would sit around forever and never be used?
That's a good question. It is that it's actually related a bit to the previous. So if you, as you say, you let the system run indefinitely and you don't enter something new, you will still have the different priority values of the items, because some of them have a higher quality value, and the one with a higher quality value have a higher barrier under which the priority cannot fall below. So in the long term, you will have the effect that the higher quality items are still processed more often than the ones with lower quality. But still, the lower priority items have still a chance to be selected, even though the chance is lower than for one which has a higher priority, or in this case, quality. There's another aspect. It will not store all the statements which it received over its lifetime, because it only has a fixed storage. So the insufficient resource assumption is really inbuilt in the system. It can only consume up to a certain maximum amount of memory. So it has a eviction strategy which is very simple. So when the bag gets full and a new item wants to get into, it simply removes the lowest priority item. When this happens, the lowest priority item will be lost, so to speak. So this is how it manages to keep a fixed size memory. And what this means in your scenario is that that a lot of input which has been given over its lifetime before it was run for some unspecified time without new input, that it's likely that a lot of information is not in the system anymore, because the memory is likely already full, and a lot of the inputs have been forgotten. So it will only think about the items which it still has in its memory, essentially. And the idea here is there are multiple things which have to be taken into account here. Ideally, we want the high quality items to be beliefs which are really useful for the system in terms of fulfilling its goals or to answer user questions. So it should keep the information which has historically been important. And ideally, this is the information the memory will fill up with over a long time period. And or the other information the new information will be there for a short moment, but if it does not turn into something useful, it will be eliminated. I hope this answers the question.
So I suppose an obvious way to tie this in with certain other AGI topics would be to introduce some sort of compression mechanism to run in the background, so that maybe Nars could compress old things to try to store them longer. And of course, this, as you all obviously know, is a rabbit hole that goes infinitely deep, and probably whole entire tomes of books could be written on the subject.
I agree. Compression is an important aspect, of course. There's also another. I mean, the counter mechanism naturally should tend to compress information, because it has this complexity bias. So concepts which are more simple and more generally applicable tend to survive better than other concepts. So there's naturally some pressure for the system to compress its experience. And the thing is, it's a bit more than just compression, actually, because if we how to say, because the information it wants to retrieve is not only describing a lot of experience, but experience which is relevant for fulfilling its goals and answering user questions. So it's a very directed form of compression, because it tries to maximize its capability in terms of goal fulfillment, essentially. And this is what the control mechanism tries to achieve on a global scale.
I have a question about how do you, I mean, does it enable multiple models of the environment, or do you have just one big model? I want to compare that, for instance, with a Solomonov induction, or more generally Bayesian model averaging, where you just have an envelope of our models. So yeah, how does that work in that respect?
I think the best way to look at it is to see each statement in the system as a partial description of what it has experienced. So it's not trying to build a complete model of the environment, in the sense that there is one model and it has to maybe adjust this one model and replace it with another model if it doesn't work. It's more like it has a lot of small tiny pieces which describe small aspects of the environment. Like if I can describe something like how can I open the door? I need to use the door handle, and this does not describe the room around me, but it describes a small aspect of the situation around me. There's a door on the other side of the room, and I can use this information to open the door. And I think this is really on the heart of, this is really the heart and soul of this conceptual representation idea. To have partial descriptions of the environment which are at the same time composable, so you can build other things with using the concepts you already have, but at the same time the concepts represent only a small aspect of what the system has experienced. And it's all those different concepts with the different priority which essentially make up the system's current understanding of its environment. So it's like a lot of tiny micro models which the system has. But the essential thing here is that the model does not really describe some external coherence like Newton's laws or something like that. Instead, those statements simply describe relationships between the patterns it has experienced. How did it experience them? Depends on how it's embedded, depends on the sensors it has, and the modalities, and so dependent on how it retrieves, how it retrieves information from its environment, and how this is structured, it will form concepts based on those experienced patterns. And so what this also means is that if you have one system which, for instance, has only vision, and the other system we only give it a microphone, and then there's a cat, one system sees the cat with a camera, the other system only hears the meowing of the cat. And one could say both systems have some kind of concept of a cat, which is this experienced pattern of what the cat looks like in one system, or for the other system, what this pattern sounds like, or what the sound is composed of, so to speak. But even though those both concepts, we would say, refer to this external cat, this is not what the system actually needs to assume, that it really corresponds to this external entity. It's more like it only needs to summarize the patterns it experiences. And so two concepts in two different systems can be composed in very different ways, even in cases where we could say it refers to the same entity in the outside world. So it actually, it solves a bit of this problem of traditional symbolic AI, which is that each pattern or each symbol has an external entity to refer to. In Nars, this is not the case. It's the relationships it builds are simply between experienced patterns without the necessity to have some one-to-one mapping to some external entity.
Well, I mean, if you consider Solomon induction, I mean, if the binary sensor is considered to be internal, well, then it's also some sort of introspective induction mechanism. But so I have a follow-up question. If you have contradictory patterns, predictive patterns, so for instance, you have one pattern to predict that the door is going to open and another one, how do you, I mean, that would be the equivalent of having multiple models for this restricted context. How do you aggregate these contextual models in order to make your final prediction?
That's a good question. Essentially, it comes a bit back to the control mechanism itself, because somehow we want the system to activate the right hypothesis when it, for instance, experiences a door. Then we want the system to retrieve the relevant knowledge. For instance, if it wants to get to the other room, it needs to retrieve the knowledge, which is this model, or this partial model, or how we would say statement about how to open, or multiple statements about how to open a door via a door handle. And what we have here is essentially, here we can make use of the compositionality of the concepts, because when the system sees a door and it sees the door handle, this door handle pattern is actually a sub-pattern of the more complex pattern, which is to say, if I press the door handle, then the door will be open. So the idea here is to make use of compositionality. In Nars memory, the system never really has to search for anything, because how things are composed together, it naturally gives the system a way to prioritize the right things in the right moment via its memory structure. So when it sees the door handle, it will automatically activate or increase the priority of related concepts. And so it will then have a high chance to inference on how to open the door if its goal is to reach the other side or the other room. So essentially, we try to avoid search, we try to exploit composition, and that's essentially how we try to address this.
So basically, by using composition, so if you have, I mean, I don't see exactly how all that works, but like I guess there's some kind of spread of importance, a priority, and you might be in the situation where from the handle you could spread equally to two different situations. Well, I can't give a concrete example because I don't know if there are multiple ways to use a handle, but well, yeah, I mean, for instance, you could have a door where you have to turn clockwise and the other one where you have to turn anti-clockwise, and you have to decide which way to go. And if you have so I mean, how do you deal with competitive predictive models? Basically, I'm still not seeing that very clearly.
The idea basically, if we think about activation spreading, as you mentioned it, it can be seen like a form of voting. At the beginning, it doesn't really, it isn't bad if we just distribute the same priority to the links, meaning to the components. So, and as long as there are multiple items which vote for it, for instance, it sees this door handle, it will activate a lot of knowledge about door handles. A lot of this information it will activate is not really relevant. Some information like how to open it will be relevant for reaching the other room. But now there is also this score to reach the other room. And this itself will prime for this door handle concept. And this is where the difference happens. Even though initially it spread the activations equally among the related hypotheses, there are multiple tasks in this case. One is it sees this bottom-up pattern of the door handle. On the other hand, it also has this score to reach the other side of the room, which via implication statements also has this door handle as a component. So this door handle will now have the highest priority among a lot of different information about door handles, which only has been activated by the experienced pattern, while how to open the door handle has been reinforced 2 times by the current observation and by the intention of the system. So by what it essentially, by its score. And this is how this is essentially done. It really tries to use this activation spreading as a voting. And this activation spreading is also not simply spread among all the links. That's also happening, but there's also spreading by inference. For instance, if the system derives by backward inference, so it wants to reach the other room, and it has multiple hypotheses how to reach this other room, and there are multiple candidates, and one of them will be to use the door handle. And so in this case, it's a backward inference, which causes the derivation of a subcore, which will then additionally prime this concept of a door handle and the related information how to open it. That's the idea. And also another relevant part here is because you mentioned this, what if you have multiple competing hypotheses? Because clearly it's not only the priority which matters. It's not just, is this currently something I see, or is this currently something I might want? This is not only the important thing, it's also important if, how true is it? Is this what I see really a door handle? How sure I am based on the appearance of this object I see? How much do I believe that opening the door handle will allow me to get to the other room? And so it's also the truth which is relevant, not only the priority, which comes to the next consideration, that whenever we derive a task, it's not just the priority of the task which led to its derivation which matters, but it's also the truth expectation of the task which matters. So if something has a so the hypothesis which has a higher truth expectation essentially will tend to be the one which causes the actual behavior. And just one moment, I will get the water.
Okay, but yeah, thank you. That was interesting.
You're welcome. And in the architecture, I think I will now already switch to my presentation. There's a simpler system we currently work on, which tries to make certain simplifications. And one of them is, for instance, if you have multiple hypotheses to reach a certain goal, simply select the hypothesis with the highest growth expectation, for instance, and which has the precondition currently fulfilled. And this is something which also the Java OpenNARS does, but there it's less restrictive. The Java version is essentially leaving it to the back selection, while in this new system, there are some pragmatic design decisions we made to make it work better for application purposes.